Welcome back to The Explainer. Today, we're taking a deep dive into the hidden structural science of the Nepal National Building Code, specifically the NBC 105-2020 guidelines. We are going to unpack the invisible, everyday math that keeps the roof over our heads exactly where it belongs, even under the most extreme conditions imaginable.
Okay, let's dive into this. It's a question we probably don't ask ourselves enough, right? When the ground is violently shaking, how does an everyday building, a place where families sleep, eat, and live, actually survive? Well, today we're framing the structural engineer not just as someone crunching numbers in an office, but as a brilliant defender against massive, invisible natural forces.
Here is our roadmap for today's explainer. First, blueprint of a safe home. Second, materials and the foundation. Third, calculating everyday gravity loads. Fourth, defending against the earthquake. And finally, number 5, the math of seismic safety. It's going to be an amazing step-by-step journey, so stick with me. All right, Section 1, Blueprint of a Safe Home. Let's set our boundaries. I want you to picture this specific building in your mind as our primary case study. It's a standard 3-story residential house. Notice the distinct architectural layout here. We've got the ground floor, the main living, bedrooms right above that, and right at the very top, a small stair cover. This physical space, this is the exact battleground where our engineering forces are about to be tested. To really test this home, engineers have to set some strict boundaries. We're talking strictly about an ordinary residential structure with a footprint under 1,000 square feet. It's a reinforced concrete frame, 3 stories tall, exactly 3.2 meters per story. And here is the kicker. Engineers actually have to assume that the brick walls, the masonry infill, offer absolutely zero contribution to resisting loads. None. The concrete skeleton literally has to do all the heavy lifting completely on its own. Moving on to Section 2, Materials and the Foundation. It's time to unpack the structural toolkit. And this brilliantly illustrates the fact that engineers don't just guess how a building is going to behave. They follow a highly methodical, highly protective sequence to build its defenses. Step 1 is strictly defining the exact material and structural section sizes. From there, they meticulously calculate every single load, run a complete digital model, analyze the stresses, combine those load scenarios, and honestly, only after all that rigorous testing do they even think about finalizing the design. Let's look at the actual materials themselves. The raw defensive capability of the house relies entirely on these specific numbers. We have concrete that can withstand 20 newtons per square millimeter of compression, and it's reinforced with high-yield steel bars. But wow, notice the immense weight here. Reinforced concrete sits at 25 kilonewtons per cubic meter. Just to put that into perspective for a second, that is roughly 2.5 times heavier than solid water. So these materials are incredibly strong for sure, but they are also profoundly heavy. Okay, Section 3. Calculating everyday gravity loads. Let's figure out the weight. Before a building can safely hold you and your family, it absolutely must be mathematically proven to hold itself up. This concept is called the dead load. It is the constant, unrelenting weight of gravity, just pulling down on the building's own materials day in and day out. It never takes a break. Look at how this actually breaks down mathematically. These are fixed, inescapable numbers pulling down on the frame every second of every day. Interestingly, the inner walls actually exert a heavier load per square meter than the outer walls, mainly because they have fewer window openings. And even something as simple as a beautiful floor finish, like the marble on the stairs, that adds a continuous 1.635 kilonewtons per square meter of force. The concrete skeleton must silently bear that weight forever. But a house isn't just an empty shell. It's meant to be lived in, and that brings us to the live load. This is where we translate strict engineering jargon into the highly relatable concept of humans actively living inside the blueprint. It accounts for all the unpredictable weights. You, your furniture, moving objects, and even that massive 1,000-liter PVC water tank sitting right on top of the roof. So the crucial point is right here at the top of this breakdown. Notice how staircases and balconies are assigned the highest live load at 3 kilonewtons per square meter, compared to just 2 for normal bedrooms. Why is that? Well, because during an emergency, the staircase becomes a critical, densely packed escape route. The engineer has to mathematically design for that sudden, panicked surge of heavy human movement. Section 4. Defending against the earthquake. It is time to simulate some massive seismic force. Structural engineering is a discipline that constantly evolves, and it often does so by reacting to past disasters. Take a look at the evolution of the horizontal base shear coefficient. Basically, this is the complex calculation for how much horizontal earthquake force the entire building absolutely has to resist. We've moved from the simpler CZKIK formula of the old 1992 code to the highly complex multivariable formulas of the new NBC 105-2020 code. It represents a massive, game-changing leap forward in safety precision. And that kind of precision is absolutely necessary, because location dictates danger. The seismic zone factor map of Nepal reminds us that geography directly determines the severity of the invisible forces acting on our case study. Those jagged lines crossing the country, they aren't just administrative borders, they represent deep, underground threat levels. For our specific 3-story building model, the code dictates a seismic zone factor of 0.35. That is a significantly high value. It mathematically demonstrates the massive foundational risk our home faces in this highly active seismic region. And practically speaking, it directly amplifies all the forces the building must be designed to withstand. Now, working right alongside the zone factor is the importance factor. Since our blueprint is an ordinary residential home, its multiplier is 1.0. However, if we were designing something like a hospital, a fire station, or an emergency shelter, this code would force that number up to 1.5. That demands an even higher threshold of structural invincibility, so those critical buildings can function seamlessly during the chaotic aftermath of a disaster. All right, bringing it home with Section 5, the math of seismic safety. Let's calculate the dynamics. Now, what's really interesting here is how a building's flexibility is visualized. These curves represent the spectral shape factor. To put it simply, this factor calculates a building's dance with a specific type of soil it sits on during an earthquake, whether that's hard rock or soft clay. Depending on the density of the earth and the exact height of the building, the structure is going to experience entirely different amplified forces over time. When we run these forces through a mathematical shortcut called the Rayleigh method, which engineers use to figure out the natural vibration frequency of a structure, we get a crystal clear picture of how the earthquake attacks. Check out the deflection data. Down at the first story, the building barely sways, just 11.54 millimeters. But those earthquake forces dangerously compound as you go up. By the time you reach that tiny stair cover at the very roof, it's whipping back and forth nearly 55 millimeters. The highest point is always, without a doubt, the most vulnerable. And through all of this intense calculation, combining the heavy dead loads of the concrete, the unpredictable live loads of the residents, and the dangerous geographic zone factors, the engineer arrives at this incredibly precise number, 0.881 seconds. This is the time period calculation. The building code literally predicts the exact rhythm at which our 3-story concrete house will safely sway back and forth during a massive seismic event. It is, quite literally, the calculated heartbeat of a surviving structure. So, we've seen how meticulously the Nepal National Building Code 105-2020 prepares a home to defend itself. The math is brilliant, it's rigid, and it's practically perfect on paper. But I want to leave you with a vital question to ponder. The theoretical engineering is flawless, but when the cement is actually poured on site, will the real-world execution perfectly match this code? Because, as we've seen, in a real earthquake, there's absolutely no margin for error. Thanks for learning with me today on The Explainer.